Okay, so let us now summarize some of the observations that we had from these examples that we looked at in the previous video. So one thing that we should remember uh, and make it a kind of a major theoretical equality to come to grips with is that a train of impulses, whether you look at it in time domain or if you look at it in frequency domain, they have the same appearance. It is a unique type of signal which looks about the same whether you have one viewpoint or the transform domain viewpoint. Specifically, if you have a train of impulses in the time domain, its Fourier transform in frequency domain is also a train of impulses, and vice versa. Now, there is a subtlety here that we should keep in mind, that although they appear the same, the details are different. Specifically, if the separation between the impulses in one domain increases, in the other domain the separation reduces. That is what we saw in the previous two examples. For example, over here the separation was smaller. Uh, Separation was 10 samples, and the separation in frequency domain was 1/10 or 1 over 10. In the second example, when we made the separation in one domain, the time domain, bigger, in the frequency domain the impulses became closer together. So that is something that we also have to keep in mind. And then the second uh, main concept that we want to keep in mind is that when we increase the separation between the impulses in one domain, in the time domain in this case, we ended up repeating the original signal but with zeros at both the ends, which is what is shown here. In this case, this rectangular signal was getting repeated one after another without any dead or blank period in between. That is because the separation between the impulses here was exactly the width of this rectangular pulse, which was 10 samples. But now in this case, we increase the separation between the impulses in this time domain impulse train. We made it 20 samples. The length of the rectangular pulse is still 10 samples. And so in the periodic signal that we got, we had this rectangular pulse, a nice rectangular pulse sticking out, but then it was padded with zeros on both the sides. There were 5 zeros on this side and 5 zeros on the other side. And that became our main period that kept on repeating every 20 samples. And it is as if, because of that, as if those added zeros that we had, that our frequency domain response got sampled in a more finer manner. What would have happened if we had made this not 20 but 200 instead? Then there will be a lot many more zeros. Actually, there will be only 10 samples of this rectangular pulse, and then there will be 190 samples which will be zeros in between two rectangular pulses. 85 on this side, 85 on the other side, and then 10 samples of this rectangular pulse. So we would have packed so many zeros in the time domain in the periodic version of this rectangular pulse. But when this 20 becomes 200, over here the impulses which are 0.05 apart, they will become 0.005 apart. So there will be so many samples of this continuous Sinc shape frequency response that we'll be getting. It is as if we'll be interpolating between these blue dots, and we'll be getting finer and finer resolution of this Sinc shape function in frequency domain. And so that is our another observation, that if we do zero padding in the time domain and then we take Fourier transform, we don't take Fourier transform of the signal right away, but we first pad it with zeros, then we make it periodic, and then we take the Fourier transform. Then what we would notice is that it is as if our original Fourier transform that we had without zero padding, it got interpolated, because we would be sampling it in a finer manner. So surprisingly, this concept of interpolation, which we can all appreciate very well, is again getting tied up with the periodicity and the notion of frequency transformation of a periodic signal. Now remember, all along we have said that whenever we make one conclusion, whenever we get hold of one insight, or we make one observation, then we always want to be agile and immediately transform our viewpoint and say what it would mean from the transform domain perspective. And so there, basically we would be invoking the duality between time and frequency, and we would say that similar to this example where we were zero padding in time domain, if we were to do zero padding in the frequency domain, then it is the time domain which will get interpolated in a finer and finer manner. So a lot of the times we would need to do interpolation in time domain, and one nice technique to do that interpolation in time domain is to actually take Fourier transformation and then put zeros on both the side of that Fourier transformation, and then take inverse Fourier transformation. Then suddenly our time domain signal will look more smoother, it will look nicer. Okay, so now let us go back to summarizing this sampling topic, and we will say that we are now going back to continuous time signal, but the observation remains the same as what we saw in case of discretized time that we were just looking at. But suppose if I have a periodic continuous time signal that now I'm calling W of t, and if I make this W of t periodic, and its period is t0 seconds, 1 over f naught, then just exactly identical to the example that we just looked at for discrete time case, we will find that the effect in the frequency domain is that the original spectrum, capital W of f, will get sampled. We will just get samples of W of f. And those samples are going to be multiple of 1 over t naught. There is a typo here. This should be n times 1 over t naught, which is n times f naught. And the Fourier transform actually becomes 0 at all the other frequencies which are not multiple of f naught. Okay, so this is a very powerful observation. In essence, what it says is that whenever you are having a periodic signal in time domain, its Fourier transform ceases to be a continuous valued function of f. In Fourier transform domain, in frequency domain, you will get samples, and those samples will be space multiple of f naught apart, where f naught is the inverse of the period in the time domain. Okay, so this f naught plays a critical role, and it is called the fundamental frequency. And all of the other samples that we get, which is an integer multiple of f naught, They are called the harmonics of the fundamental frequency. Now, how to understand it in an alternative manner? What we say is that whenever we have a periodic signal with a period of t naught, which is 1 over f naught, it cannot be made up of any complex exponential waveform whose frequency is not either f naught or it is not a multiple of f naught, integer multiple of f naught. In other words, the constituent exponentials, complex exponentials that together collectively make up this periodic signal with period of t naught, they all need to have ultimately a period of t naught also. You cannot make a periodic signal with a period of t naught by using some other periodic signals whose period is not t naught. If you think about it, it makes sense. I mean, if you have a periodic signal, let us say periodic signal has a period of 10 seconds, the only way that you can make that periodic signal, you can synthesize that periodic signal, is by taking other periodic signals whose period is also 10 seconds. If you try to make that periodic signal up, if you try to make up that periodic signal by using some other periodic signal whose period is, let us say, 7 seconds, or 11 seconds, or 13 seconds, or even 10.5 seconds, you will not succeed, because there is no way that you can get a period of 10 seconds using a periodic signal whose period is 10.5 seconds. The way to think of it is that if you want to if you are constrained to only use yellow color, for example, and if you are constrained to mix up only maybe multiple tubes of yellow color, then after mixing up all of these different yellow colors, you will again get only yellow color. You can't get any green or red color, because you are only using yellow colors in the mixing. Alternatively, if you take yellow color and if you try to find out what it is made up of, you will find that it is made up of other items which are also yellow in color. You can't have suddenly some green thing popping out of something which is entirely yellow. So that is what is going on here. Now Fourier transformation, because now it is sampled, it is given essentially as a train of impulses whose impulses are f0 hertz apart. Additionally, each of this impulse has a weight, which is denoted here as C of n. And the C of n is nothing but the Fourier transformation of this signal, periodic signal W of t, evaluated at n times f0, evaluated at n times f0, which is f of n. Furthermore, the Fourier transformation, we need to compute it only over the fundamental period only. The integration limit goes from 0 to t0, or it can be minus t0 by 2 divided by up to t0 by 2 plus t0 divided by 2, but it doesn't have to go beyond the fundamental period of t0. And we will need this division by 1 over t0 here. Again, this t should be t0. It's a typing mistake. So this is the formula for the Fourier transformation of a periodic signal. This is, remember, this is for periodic signal. If it is a periodic signal, we have to go back to our original Fourier transformation formula. Then the inverse Fourier transform now is simply summation of complex exponentials where each one is weighted by this C of n. So both, I think the inverse Fourier transform makes a lot of sense. All it says is that this periodic signal is made up of a bunch of harmonics of this fundamental frequency f0, where these different harmonics get weighted by different complex coefficients C of n. Uh, so now let us make a summary what happens with aperiodic and what happens with periodic. So for aperiodic signal, our Fourier transform or the analysis equation looks like this. We have seen this earlier. It's just a specific case of the Laplace transform. However, when the signal becomes periodic, the Fourier transform is given by this formula over here. By the way, there are multiple typing mistakes again here. I will clean this up in the next round, in the next revision of this PDF. So one mistake is that this should be W of n times f naught, because we are using n times f naught as the frequency here. This should be n times f naught. The second mistake is that the limits of integration are wrong. It should be only from minus t naught divided by 2 to t naught divided by 2, or 0 to t naught. And the third one is that we need to do 1 over t naught here. We need to divide the integral evaluated over a period of t naught seconds. We need to divide it by t naught. So there are multiple mistakes in this equation. Please keep that in the mind. In the revised version, I will correct these mistakes. Now, if you look at the inverse Fourier transform, this is the formula for the aperiodic signal, aperiodic continuous time signal. Whereas inverse Fourier transform for a periodic signal becomes just a series, summation. The integration is getting replaced by summation. The reason this is happening is because the frequency axis has been discretized. It is not continuous anymore. And so therefore the integration becomes summation. Okay, so that is kind of a formal way of appreciating the effect of introducing periodicity in time domain. What happens when we introduce periodicity in frequency domain? We have seen here already in this section, effect of sampling. So there is a nice dual aspect to this. If you make the frequency domain periodic, then the time domain gets sampled. But that time domain sampling is very much of benefit to us. As we said, it is kind of the very first block where the analog signal gets converted into a digital signal in the A to D converter, analog to digital converter. So that part is covered here in this section, effect of sampling. The dual part is that now instead of making frequency domain periodic, we are here in the Fourier series, we are making the time domain periodic. And when we do that, the frequency domain gets discretized, as it is shown here. So again, we are flipping back and forth between two dual interpretation of the periodicity and the sampling. Now, before we move on to the next topic, I just want to bring to your attention that this equation here, W of t, written as a summation of complex exponential, where each exponential is weighted by this complex coefficient C of n, which is nothing but the Fourier transform evaluated at n times f naught of this periodic signal. So this representation of time domain signal, it can be in an equivalent manner, can also be written by using not complex exponential, but instead by using cosine and sine. So this equation here is same as the equation over here. Or instead of using cosine and sine, we can also get the expression of Wt using what is known as the polar coordinates. So in one case, we have used the notation C of n. The other case, we have used notation A of n and B of n. And then In the third case, we have used the notation capital D of n and phi of n. This symbol represents the phase phi or phi, you can pronounce it either way. And it turns out that there is a relationship between A's, B's, C's, and D's, and that those relationships are written over here. Uh, by using your simple complex uh, mathematics, you will be able to prove all of these equations. So I suggest that you yourself try to derive these equations. All that you have to do is to realize that this complex number C of n has Cartesian representation in terms of A of n plus j times B of n, and it has polar representation in terms of D of n and phase phi of n. Okay, so now let us continue our discussion forward, and now we will summarize this duality properties of Fourier transformation. What happens when you do when you consider periodicity in time domain? What happens to its Fourier transformation? All of that we are going to now summarize by taking one more visual example, and then that will be the conclusion of this topic that we have embarked upon, which is how the periodicity in one domain causes the other domain, the transform domain, to be sampled. Okay, so we are going to now take the Fourier transform of a continuous time rectangular periodic waveform. Before we do that, let us recall the Fourier transformation of a continuous time aperiodic rectangular signal. We have done this earlier as it is shown in this slide. This is a continuous time signal, it is aperiodic and it is rectangular in nature. And we have seen that its Fourier transform is this Sinc function. And we have seen that if I make this capital T bigger, the Sinc function becomes shrink in frequency domain, as it is shown here. So the width of this pulse determines how wide the Sinc function is in the frequency domain. If I make the width of the time domain pulse bigger, the frequency domain Sinc function will become shrink, it will become compressed. The second thing that we have noticed is that if we take that rectangular signal and if we make it periodic, then effectively our Fourier transform will get sampled. And the interval between those samples will depend on f0, which is 1 over the period in the time domain. So these two observations are being shown pictorially here. I have a rectangular pulse, which is this here. The width of the pulse is 5 millisecond. And I have made this rectangular pulse periodic, whose period is 50 millisecond. Now, therefore, I get in frequency domain a Sinc profile. This is the magnitude of the Sinc. And so negative values have become positive now. The width of this main lobe of the Sinc is going to be inverse of this 5 millisecond width of the rectangular pulse. Inverse of 5 millisecond is 200 hertz. And so you can see that the main lobe is 200 hertz on each side. And then you get another lobe from negative 200 to negative 400, plus 200 to plus 400, and so on. And so the width of this pulse determines the width of the main lobes and what are known as the side lobes of the Sinc function in frequency domain. But you will see that this function is not this continuous valued rad dotted function here. In fact, it has been discretized in frequency domain. I see samples in the frequency domain. And the separation between these samples in the frequency domain is exactly inverse of the period in time domain, which is 50 millisecond. The inverse of 50 millisecond is 20 hertz. And so the separation between these two samples in frequency domain is exactly going to be 20 hertz. Effectively, there are going to be 10 samples in this log. 10 samples going from 0 to 200, which are 20 hertz apart. 20 hertz is inverse of this 50 millisecond. So now we can do some experiments. What happens if we make the width bigger? So it has now become 10 millisecond instead of 5 millisecond. Remember, the width of this pulse directly determines the width of the sinc function in frequency domain. Here I made the width twice as bigger, so the sinc function shrank and became half as wide. Previously it was touching zeros at plus minus 200 hertz. Now it is going to zero within plus minus 100 hertz. In time domain, although I made the width of the pulses twice as much, I didn't change the period. You will see here, it is still 50 millisecond. And therefore the frequency domain impulses are still 20 hertz apart. It's just that the sinc function became thinner, more compressed. If I make the time domain pulse even larger, instead of 10 millisecond long pulses, if I make them 20 millisecond long pulses, the sinc function becomes even more shrunk. But the thing to be noted is that the interval between the impulses in the frequency domain is still exactly 20 hertz, inverse of 50 millisecond, because that part is remaining unchanged. But now what happens if I go back to this case? The width of the pulses is 5 millisecond and the periodicity is 50 millisecond in time domain. In the two examples that we looked at, I didn't change 50 millisecond. The periodicity is still 50 millisecond in time domain. I just kept on changing the width from 5 millisecond to 10. I made it 10 millisecond and then I made it 20 millisecond. Now let us see what happens if I keep the width to be 5 millisecond only, but instead of that I change the periodicity, and instead of 50 millisecond I made it 20 millisecond period. In other words, the period in the time domain has shrunk because the period has reduced. The spacing between the impulses in the frequency domain has increased, and now it has become 50 hertz. Remember, it was 20 hertz before with 5 millisecond period. With 20 millisecond period, it was 20 hertz with 50 millisecond period. When I made the period to be smaller and made it 20 millisecond, the interval between the samples of the frequency domain has now become 50 hertz instead of 20 hertz. So this is the Fourier series representation of this rectangular pulse. Okay, so we will stop here and we will resume the last and the remaining topic of this Fourier transformation when we take up this video session next time.